professor from Duke University. Yeah, and he will talk about Nahm transform old and new. Yeah, let's welcome.
Thank you. It's a pleasure to be here. I'd like to thank the organizers for inviting me. I always enjoy having a chance to be back in China. All right, so today I want to talk about the Nahm transform, and this plays a fundamental role in studying instanton moduli spaces. So moduli spaces of Yang-Mills instantons and monopoles play a really important role in high-energy particle physics, in algebraic geometry, and in low-dimensional topology. And in this in this talk, I won't talk about the applications of the moduli space. I'm just going to talk about how to probe the structure of it, which is what the Nahm transform is used for. I should also mention that these moduli spaces are also a rich source of manifolds, typically with special holonomy. So for people in the special holonomy world, these spaces are also of interest. Okay, so we want to use the Nahm transform to probe the structure of these moduli spaces. And so what I want to do in this talk is start with an alternative history, I'll say, of the Nahm transform, some history as it should have been, maybe. And I won't have time I won't spend much time on the real history. And then I'll quickly move to recent questions and recent progress since the study of the Nahm transform. And then I hope, since I see there are lots of young people here, to have some time to discuss accessible questions that are open for immediate attack. And as I said, so due to time constraints, I, of course, will necessarily omit most of the genuine history of the Nahm transform. So many people have worked on this area. Okay, so a brief course outline. First, I'm going to discuss what I call the zero-dimensional Nahm transform. And then I'm going to go to the more standard geometric Nahm transform that folks in the domain are familiar with. Then I'm going to talk about the work that I've been focused on. So we have a series of several papers for the last several years discussing how to extend the Nahm transform to gravitational instantons known as ALF spaces, asymptotically locally flat spaces. And then so I'll discuss the Nahm, I'll introduce those spaces, then discuss the Nahm transform for those spaces. And again, depending on how much time we have, then I'd like to end up with some questions for the younger folk to attack afterwards. All right, so first let's start with Nahm in dimension 0. So this is really representation theory, in particular the Borel-Veil-Bott theorem is generalized by constant. So in representation theory, there's been a fundamental problem or question that people have asked for years, which is how to realize representations of groups, especially Lie groups, geometrically or topologically. And Borel-Veil-Bott, generalized by Constant and even more by Atiyah Schmidt, showed that many representations can be realized on cohomology of manifolds. And so you can understand irreducible representation as some particular cohomology group for manifold. And then using the Hodge isomorphism, you could go from cohomology, realizing representations in cohomology, to realizing them in the kernel of a Laplace type operator, or perhaps more generally a Dirac type operator. And so that's what Borel-Veil-Bott, Constant, and Atiyah Schmidt have done. And so let me give you a very classic example of this. And I'm not sure where Borel-Veil-Bott ended off and Constant picked up, so I'll just attribute to all. So first, suppose E lambda is an irreducible representation of the unitary group with highest weight lambda. Then there's some algebraic manipulations you can do associated with the highest weight to construct a homogeneous holomorphic vector bundle, which I call calligraphic E lambda, over the Grassmannian manifold, so the Grassmannian of K-planes in Cn. And then if you look at the cohomology, sheaf cohomology in degree 0 of the Grassmannian with coefficients in this homogeneous holomorphic vector bundle, then you get back the original vector space you started with, E lambda. And this equality is not just equality of vector spaces, so it's not a dimension statement, but it's equality of UN representations, so UN modules. And let me specialize a little further. Suppose we let U be the universal CK bundle of the Grassmannian. So at a K-plane, the fiber is that K-plane. And let DU denote its canonical connection. Then you can split DU as a D bar operator. This is the part that raises the DZ bar degree, and the part, what I call partial U, the part that raises the DZ degree. And you can look at the DU plus DU star defines a Dirac operator. And if you look at the kernel of that Dirac operator, then it's Cn, again, as a UN module. And in this case, it's really easy to construct the UN equivariant map that identifies Cn with the kernel of that Dirac operator. So let me go through that. So we can view the Grassmannian of K-planes in Cn as just the submanifold, the rank K unitary projections in the Euclidean space of all Hermitian n by n matrices. So it's that makes it easy for a Riemannian geometer to understand. And if we'll define kappa, the elements in this kernel, this is not, there we go. Can't really see that. Huh, interesting. Elements in the kernel, the old-fashioned pointer. Elements in the kernel are, of course, sections. So to tell you what a section is, I have to evaluate it at a point. I'm denoting the points on the manifold by pi, the projections. So I have to tell you how kappa, when it eats a vector in Cn, how to evaluate on the point pi, at the point pi, and it's just pi of v. So pi was a projection, so I'm just taking v and projecting it onto the image of pi. And that's obviously an injective map from Cn to some set of sections. It's an easy computation to show that I've given you a kernel of a Dirac operator. And I'm not going to do the computation here at the board, but ultimately it boils down to the fact that pi is just the restriction of a coordinate function in the ambient Euclidean space to a submanifold. And if there's any function we know how to differentiate, it's a coordinate function. And so it's easy to do the differentiation, and you can compute that we've actually constructed something in the kernel of this operator. So then I claim I have a UN isomorphism, so I have to tell you what the action of UN is on sections. So the action is going to be, UN is going to act on the base manifold, and then you're going to have an action on the fiber. So let's just write that down. So we write rho g of kappa v of pi. Well, it acts on the base manifold by conjugation. So there's the action on the base. And I have another pointer in here. Maybe I should use that. And then an action on the fiber just given by the usual action of G on Cn. And if you remember that kappa v was just taking G inverse pi G and acting on V, then it becomes this next line. And then when you undo the G's and G inverses, you just get pi of GV, which then is kappa GV of pi. So we've just intertwined rho G of kappa is kappa of GV. So just a trivial computation. So we see that's UN equivariant and clearly an isomorphism. Okay, so let's call kappa the BWB map for Borel-Vaibhav. So we'll be hitting this multiply. So let's recap what we've done. I started off with the data of, in this last example, of the vector space Cn. And I'm thinking that for generalization purposes, I'll think of that as a vector bundle over a point. And then I associated to that the space of all k-dimensional subspaces of Cn and the canonical bundle over that. And that's first association I call N1. And then given that second piece of data, I've associated the kernel of a Dirac type operator, which is then again a vector space, but I think of that as maybe a vector bundle over a point. And then finally, this map kappa, although the way I've written it must be kappa inverse, tells me that I had the same thing I started with, Cn over a point. And so this is, again, a special case of this general notion of representation theory. Can you understand representation, any representation as a kernel of a Dirac type operator? And then now what we want to do with the Nahm transform is look at a family's version of that. So can I now, if I have a nice vector bundle, can I realize the fibers as families of kernels of Dirac type operators? And so, so we're going to replace the vector space, which had a Lie algebra action over a point, with a vector bundle. The Lie algebra actions can be replaced by a nice connection, and the points can be replaced by a manifold. And so I'm going to ask, can we geometrically realize nice vector bundles with connection as families of kernels of nice Dirac type operators? And this is what the Nahm transform often gives us. Yes? Please do. I meant to comment on that. Thank you for this. Is as though you had my notes and told me I missed something. So I appreciate that. So in this picture, I can replace the Gross. You can think of the Grassmanni of K-planes in Cn as a two-step flag manifold, and you can replace that with longer flags, giving you a higher dimensional base space. When you do, that'll change the rank of the bundle U I have over that's associated. It'll drop in rank. And so I can change this picture where these two guys change. This gets higher dimensional, this gets lower rank. I still get the same thing here and the same endpoints. Okay, so there's a large family of such things that give me the same endpoint. But this is the one that looks most like Nahm transform. So a question I was going to ask later, but I'll ask now since you mentioned this, is I'm curious for some of you young folk to figure out whether there's different flavors of the Nahm transform if you model it not on the two-step flag, but on a longer flag manifold. So it would give you different notions. You have the same thing, this Borel-Bott type picture. Do you get different flavors of Nahm transform if you model it in different spaces? I think that's my next comment. All right, so now that's my representation theoretic background. And for those of you who don't like representation theory, well, now leave it behind. But you know you should learn representation theory. Everybody has to know representation theory. Okay, so let's jump now from 0 to 4 dimensions. And so we had all these nice Lie group structures, and we need to replace them with manifolds that have special geometry, and we'll look at vector bundles with special structures on them. Because we can't hope to just go from such homogeneous things to things with no structure whatsoever. Okay, so first we'll need instantons, but before we get to Yang-Mills instantons, let's start with gravitational instantons. So henceforth, I want M to be an oriented, four-dimensional, complete, non-compact, hyperkähler manifold with quadratic curvature decay. Quadratic curvature decay comes up again and again in these situations. And for those of you all who haven't done much geometry yet, hyperkähler means you have a basis, if you like, of three different complex structures that interact the same way the unit quaternions I, J, and K do in terms of their actions. All right, so let's recall that these gravitational instantons come in 4 families. The first family are the ALE spaces, asymptotically locally Euclidean, and they have quartic volume growth, and they're asymptotically of the form R4 mod out by a finite group. So pretty easy to understand. The next family, the one that I'm going to talk about today, are the asymptotically locally flat, or ALF, gravitational instantons. Those have cubic volume growth, and they're asymptotically the form of a S1 bundle over R3, or maybe a finite quotient of the same. Next, for completion, I'll add the two collections I won't talk about. They're the ALG or ALG and ALG star instantons, and Now those I don't think stand for anything. People just liked E and F. They figured G came next. And so they have quadratic volume growth, and they're asymptotically warped T2 bundles over R2. Our quotients are the same. And finally, ALH and ALH star are gravitational instantons with subquadratic volume growth. Okay. So because these manifolds are hyperkähler, they're in particular Ricci flat, and therefore the natural playground for many problems in gravitational physics. Okay. So in recent years, there's been a program to understand the moduli space of Yang-Mills instantons in these spaces. So there's been an enormous amount of work people putting in trying to understand how to understand these spaces. The moduli spaces associated with these, and also how to understand these objects as moduli spaces themselves. And again, once again, the Nahm transform is the primary tool for trying to understand these. So let's now bring in the Yang-Mills instantons. So I'll let let E be a Hermitian vector bundle, and dA a metric compatible connection on it. I'll usually not mention the metric. There's just one in the background, and my connections are always metric compatible. So I call EDA an instanton if it's curvature, so my dA, I always think of my connection as being the analog of the exterior derivative. So if I had the usual exterior derivative, of course, it squares to 0, but when I have a connection, it squares to the curvature. And an instanton, the first requirement is that the curvature be in L2. I don't like to call things instantons if they're not L2. And secondly, we remember in dimension 4, so the Hodge star operator takes a 2 form to a 2 form, splits the 2 forms into the plus and minus eigenspaces of the Hodge star, and I'm assuming that my curvature is always in the minus eigenspace of the Hodge star. If you don't have a distinguished orientation, then of course you can always rig your orientation. If you had if you were in the plus, you can be in the minus. All right, so suppose we start off with an instanton. We're also going to need the spin bundles on the manifold N. So let's let S plus and minus be the positive and negative chirality spin bundles respectively. And I'll mention that in the case of these gravitational instantons, S plus is typically a trivial bundle. So it's just C2 cross M, or M, I guess, M cross C2 in my notation. Although S minus will not be trivial. All right, and so when you have the Riemannian connection on S plus and minus, you can couple that to the bundle connection, and that allows you to define a Dirac operator from sections of E tensor S plus to sections of E tensor S minus. And the Lishnerovitz formula tells you d dagger d is nabla star nabla plus the curvature, the Clifford multiplication by the curvature of F, plus a scalar curvature term, which is 0 in our case. Cap over 4 there is, I could replace by 0. Since in this instance, let me see if I can get no, okay. Since we are Ricci flat, the curvature is 0. So using that, it's easy to deduce. The curvature, the CF term acts trivially on E tensor S plus. It's just a computation. And so from that, it's easy to deduce that the kernel of the Dirac operator is 0. So we'll need that fact again, and we'll see it again. Yes, sir. Why is it trivial? Yes, so you can use you can use the complex structure operators that are covariant constant. It's not too hard to use them. They're going to be they'll give you the triviality of it. Okay, okay. So now where am I? I want to talk about how to construct a Nahm transform. So we're going to start off with some instanton, EDA. And now I want to probe it with a family of instantons. So for this to be useful, the family needs to somehow be simpler. So the instantons are typically either just abelian, either it's just line bundles where all your PDE reduces to linear PDE, and so life is simple, or maybe even flat bundles where it's just topology. This is a geometric analysis. This is geometric analysis, so the topology becomes trivial. And so we'll let LB be auxiliary, the auxiliary this family of Hermitian bundles. I said typically of a simpler structure, and DB is going to be a connection. And the B is in some parameter space M hat. And I said connected parameter space. I might want to withdraw that in a minute. Anyway, you can couple the connections together, and E tensor LB gets then an instanton connection, inherits from the two the connections on the two factors. So we then have, once again, a Dirac operator from the bundle tensor S plus to the bundle to tensor S minus. Again, we have the Lishnerovitz formula tells you the kernel of the operator DB is 0. But now, because index theorem tells you as long as these operators are varying smoothly, so let's think of L for a minute as being, on each component of M hat, it'll have a fixed topological type, and really I'm just going to be varying the connection. So I have a smoothly varying family of operators, so index theory tells you the index is constant rank, which then implies that the kernel of the adjoint of the Dirac operator has constant rank, and therefore you can use it to define a kernel bundle, which I call calligraphic E, on M hat, or gives you a bundle in each component of M hat. And that bundle has a canonical metric and a canonical connection. So let's say a little bit about the canonical geometry. So on each component, those LBs we said had a fixed topological type, so I just write it as L's and drop the subscript. And then on those components, we have this. So this really should be each component of M hat. But we'll consider just the one component case for now. So we have M hat cross L2 is just a trivial Hilbert bundle. So it's infinite dimensional, but it's trivial. And as trivial bundle has a canonical trivial connection. And so calligraphic E inherits a connection because it's a subbundle of this trivial bundle. So we can just give it a connection in the following way. Let's let pi at B denote the unitary projection from L2 to the kernel of dB dagger. Then we just take pi and create a connection sandwich out of it. So we define d sub pi to be pi dl2 pi. And that gives us the connection on E. And so we call the pair calligraphic E d pi a Nahm transform of EDA. I say A rather than the because it depends on the family of auxiliary bundles that we fed in. And the expectation, what you're always trying to prove when you play this game, is that the Nahm transform takes an instanton, a bundle with instanton connection to a bundle with instanton connection. I fudged it here to talk about instanton structures because typically you have to leave slightly the familiar realm of vector bundles a little bit to see what's going on. Okay, so remember we introduced the Nahm transform as a probe of the structure of the moduli space. So if it's a probe, this Nahm transform better has some nice properties. And in particular, what we'd like to do is somehow use the structure of the moduli space of instantons on the image to understand the instanton space, moduli space we started with. So for that, we really need that the Nahm transform is bijective and hopefully has more structure than that. So bijection is good, or even better. It'd be nice. It's nice when it's a modular. It's an isometry between a the moduli spaces. These moduli spaces come with canonical metrics. So this is most often proved, as with the Borel-Weber theorem we started with, by proving that if you apply a Nahm transform twice, then you compose with that kappa map, or maybe perhaps its inverse that we introduced earlier, that we get the identity for some suitable BWB map kappa. And let me just mention in passing, because I didn't know where else to pick this, that when we generalize kappa to this situation, before, remember, we were focusing on the fact that it was UN equivariant, and that means somehow it was commuting, in particular at the Lie algebra level, with the action of some vector fields. So the analog of that should be that it's covariant constant in the way that makes sense. So it commutes with the relevant covariant derivatives. All right, but there's a problem here, which is that Nahm composed with kappa inverse equals the identity only makes sense if M is also a parameter space for a family of Dirac type operators on M hat. So that's part of the reason why people have worked so hard in recent years to understand the gravitational instantons as moduli spaces of interesting objects. So when M is an ALE space, the Nahm transform analysis in the general ALE space case was executed by Kronheimer and Nakajima. And in this degenerate case where you're just talking about R4, then of course Atiyah, Drenfeld, Hitchen, and Manin worked out the relevant transform in that context. And that case is very algebraic. It's like somewhat like the Grassmannian case in that ultimately you're relating you get a map between the moduli space of ASD connections to some collection of matrices, which you can think of as, again, data associated with a point, a collection of matrices satisfying algebraic relations. And I'm not going to say anything more about that here because we don't have time, and that's a whole different story. And then there are various flat limits. So when you look at the degenerate case where you're just looking instead of the general gravitational instantons, where you're just looking at quotients of R4, then there's been work done on the ALF, ALG, ALH spaces by a lot of authors. My work is most inspired by Nakajima's. Oh, I guess I left out Nahm. He's on every slide, but I forgot to put him in this list. But of course, Nahm. And then there's Hurtubise and Murray and Donaldson and Hitchen. In the ALH case, there's Charbonneau. In the ALG case, there's Mochizuki and Jardim and Picard. And then there are many others. The list is long, and there's been lots of good work done in these areas. Yes. But even for the case, this one of the earliest cases addressed with the Nahm transform techniques, R3 cross S1, and also the associated case in monopoles, all the work done until our work left lots of holes in the theory, in that it wasn't clear that the entire moduli space was reached by the Nahm transform as it existed. So in our work on ALF spaces, we sort of filled in a lot of holes in the literature. All right, so for the remainder of this talk, I'm going to discuss just how to execute the Nahm analysis for the AK-type ALF spaces, which are just more familiarly the multi-center Taub-Nut spaces. So now I'm going to introduce multi-center Taub-Nut. It's geometry briefly, and then a lot of work will be done, some of it somewhat sloppily due to time constraints, to see it as a moduli space, since we're going to have that always the issue. We need to have the space we're working on also a moduli space of some form if we want to do Nahm twice in a row. Okay, so what is Taub-Nut if you haven't, multi-center Taub-Nut if you haven't played with it recently? So first of all, it's a bundle. Excuse me. It's a degenerate circle bundle over R3. So if you take out k points in R3, call them nu sigma, sigma running from 1 to k, then pi outside of those K points is just a circle bundle, and the circle fibers collapse at those K points. And it has a metric of Gibbons-Hawking type. So the metric G is V times just the pullback of the usual Euclidean metric on R3 plus V inverse times d tau, where d tau is just a coordinate in the circle fiber, and some connection term, pi star omega. And V is a harmonic function, as usual in this case, and it's the form a positive number L plus a sum of K harmonic source terms. And the connection term omega satisfies D of it is the three-dimensional Hodge star of dV. Okay, so that was the geometry of the space, but now we need to understand it as a moduli space too. So to understand it as a moduli space, we go to Cherkas's bow construction. So Nakajima had introduced quivers to study similar results in the ALE case, and so I guess Sergei wanted bows to go with the quivers, and we need arrows for, I don't know whether arrows two are taken already in mathematics. Anyway, so we'll realize this multi-center Taub nut as a hyperkähler quotient of an infinite dimensional quaternionic affine space given by Sergei's small bow data. But before we introduce the small bow, let's start with the general bow, because that'll also play a role. And again, we'll want to introduce their affine hyperkähler space of data. And I'm going to not show you most of the material here because it would get us very lost at the board. And if anybody's interested to know the details, the papers are all online. 2 out of 3 of them are published in JDG, and the last one's was put up last summer on the archive. So a bow consists of the following data. So we're going to have some circle of, say, length L. And on that circle, we're going to have K marked points, which I'm calling P1, P2, P3, and my K is equal to 4 in this picture. And then between those K points, we'll have intervals I sigma going from P sigma minus 1 to P sigma. And then in addition to those P points, we have we have lambda points. We have the red and the blue. So the P points are somehow associated with the geometry, the way you should think about it. The lambda points are going to be associated with the vector bundle data. Okay, so the P's encode the geometric data, the lambdas encode the bundle data. So we have endpoints lambda 1, lambda 2 through lambda n. They're required to be distinct from the PIs. And no two of them can, and they're also distinct from each other, so no multiplicity is allowed. And n can be 0. Yeah, so it's not necessary for lambda could be an empty set. All right, so associated with that picture, I'm going to introduce the bow data for this AK-1 bow. And so the bow data first gives us a Hermitian vector bundle. I'm calling it calligraphic E again. I hope that doesn't cause trouble. And it's a collection of Hermitian bundles on each of the line segments. If you take the complement of all those red and blue points, and those give us a bunch of line segments. And in each of those line segments, I have a vector bundle, which, of course, for a line segment is always trivial. So we just have some family of trivial bundles, but I'm allowing it to jump on each line segment. That's why I was saying before with my M hat, I was going to fudge later on whether my moduli space was connected or not, my parameter space was connected. So in addition to the bundles, I have Nahm data. And so that's going to be a connection for these bundles. And then I'm going to, as usual, if you've played with Yang-Mills, when you go in lower dimensions, you have some residual data from connections when you've done some reduction. So I'm going to have 3 Hermitian sections, T1 through T3 of the endomorphism bundle of E. And you should think of these as sort of ghost connections. And then the part that, so this, for people who've played a lot with Nahm transform 1 and 2 or fairly clear. There's also a lot of boundary data, which I'm not going to write anything down about. I'll just say a few words. But it's going to play it plays an important role in the story, but I won't give you any explicit formulas for it. And so the first two bits of Bow data, the bundle and the Nahm data, allow us to define a Dirac operator. Remember, S plus was trivial before, a trivial C2 bundle. Now we're going to replace that by just a C2 bundle. And so we get this Dirac operator on C2 tensor E. You should think of that as like S plus tensor E. And the Dirac operator is just going to be our connection, plus we have a sum ij tj times the square root of -1, where the ij's are just an oriented basis of imaginary quaternionic units. So if I wasn't summing, I just would have said I, j, and k. All right. Now, the boundary data also is used to determine the domain of the Dirac operator. So I've introduced a Dirac operator, but I've got all these boundary points. So the boundary data is used to determine the boundary conditions. And when I finally understood this, having read Sergey for a while, I was really interested in the fact that it does it in such a way that somehow the boundary conditions are metrized. So that's sort of, to me, that was an odd phenomenon. Okay, so again, the Bow data has that sounds to me like a name of an actress or something. The Bow data has the structure of a quaternionic affine space. So we have a group of H1, in the sense of Sobolev H1, unitary sections of endomorphisms. They act by conjugation on the Nahm data and on the suppressed data. And this gives rise to a hyperkähler moment map mu. So we consider the Bow data to be instanton if it satisfies the moment map equations. So that's how we define instantons in this context. And when you work out what those mean, and I will not do it at the board, that tells you in particular, you get the familiar Nahm equations. I DDS of T1 is equal to the commutator of T2 and T3, and then cyclic permutation is the same. And then there are also additional restrictions on the boundary and transmission data that arise from the moment maps. All right, so what is small Bow data? So small Bow data is a situation where all your vector bundles have rank 1, so they're just line bundles, and you have no lambda points. So you just have the geometry, no really interesting bundle structure. Then the Nahm equations dictate that the three Hermitian sections, Tj, are constant when the data is instanton. That's clear from this picture because in the U1 case, of course, 1 by 1 matrices all commute, so we get nabla DDS is 0. So the TJs are constant, and then additionally, that would tell you they're constant on each interval, but the constraints on the boundary data also tell you they're constant across the intervals too. So they're constant overall. And just some foreshadowing, you can think of the TJs as giving you coordinate functions on R3. And you can think of the connection term IT0 for the nabla DDS to give you an extra circle fiber parameter. And those later on will essentially be constructing our tau nut for us. All right, so we have some groups and quotients to think about. So in this, we're still in the small Bow case. So our H1 group of U1 gauge transformations acts on the small Bow data as before. And we can then take the hyperkähler quotient. So I called my small Bow data B for Bow. That was I don't know what you call that kind of G, but we take the hyperkähler quotient of the data by G, and that's mu inverse of nu for nu at an appropriate parameter mod G. So the nu's will correspond, the choice of mu will correspond to moduli for the multi-center tau nut spaces. So we have many possible choices of nu, and those precisely correspond to the many moduli in multi-center tau nut. So remember, our tau nut also was indexed by a nu, so it's essentially the same nu. So once again, we can think of this as an analog of the LBs we had before. This is twisting data, so we can take the Dirac operator we had before and now modify it by our small bow data, and we get a new T parameter family of Dirac operators minus nabla DDS. Did I forget my minus previously? Plus IT naught, plus, again, we just shift the previous Nahm data by our TJs. So if we do a partial gauge fixing, that allows us to quickly reduce this infinite dimensional hyperkähler quotient to a finite dimensional quotient. And we prove the following theorem, that the multi-center Taub nut is the hyperkähler quotient of the space of the instanton small bow data by G. And I should have said they're at level nu. Yes, I guess I did. The choice of moment map level set determines the nu in the Taub nut. So that tells us that this is a good setup for doing Nahm transform, because now we have a moduli space going in two directions. And since we've realized that multi-center Taub nut is a hyperkähler quotient, that naturally gives us a family of anti-self dual line bundles, sort of that they're just given to you from the construction, that are parametrized by the points S in the bow. And once again, the topological type of the LS is going to be constant on each of the open intervals that we introduced before, but can jump at each p sigma. And so this family LS-DBS determines a Nahm transform, which we call the down transform, just to remind us that we're dropping dimension from 4 to 1. So we let DS be once again the, oh, I switched sides for my spinners, sorry. And we get the kernel bundle once again, calligraphic E. It's going to be the kernel of that Dirac operator. And we'll let pi of S be the projection onto that kernel. And now we have an additional, I said we have the ghost data, the ghost connection term. So in addition to the connection which we constructed before, we'll also define these endomorphisms Tj, and they're the form a coordinate sandwich, so pi, xj, pi. And there's additional bow data, which I'm going to suppress, but arises from more pi sandwiches. Okay, so when I was first writing this talk, I realized I was putting theorems up that weren't quite true because there's important details about holonomy assumptions. So before, we were just assuming that the curvature was an L2. And here's where we filled a large gap in the literature. So a delicate analysis shows the following, sort of a local generic to global generic principle. If you have a single ray in R3, so if the holonomy of the connection in the fibers of our Taub nut projection, that's a small pi, not a big pi, over that ray has distinct limiting eigenvalues, say e to 2 pi I lambda 1 through lambda n, then in fact, along any ray, you limit to distinct eigenvalues, and they all with the same, and the limits are all the same. So when that's true, that tells you that we say that that this bundle has generic asymptotic holonomy. And a theorem says that if you have generic asymptotic holonomy, then the curvature decays quadratically. This is once again, remember, the quadratic curvature decay keeps entering. There are many, many things you want to prove in the when you're doing the Nahm transform that require knowing asymptotics. And if the curvature is bigger than that, then it's really hard to understand how that happens, how to prove such things. And in the degenerate limit, this inverse square law extends to Calorons and monopoles. All right, so as I said, this quadratic curvature decay is used over and over again in justifying aspects of the Nahm transform story. All right, so the assumption that the holonomy eigenspaces are eventually all one complex dimension implies that outside a compact set, E splits as a direct sum of eigenline bundles. And the connection respects this splitting up to order O of r to the minus 2. And in fact, we can write out explicitly the asymptotics of the connection up to order r to the minus 2. And so the eigenvalue enters in the connection term here. There's also a subleading term, mj over 2r, where mj is an integer. And then there's some pulled up of special connections from the base space. As a special case, we have the bundles we introduced earlier, the ones that came naturally with our hyperkähler quotient. Their asymptotics, which you come not from my theorem, but they just come from the direct. You compute it directly from the hyperkähler quotient. It's a special case of this where the Lj is replaced by S. Okay, so that's somehow the important pickup from that. And that ms is just the number of p points between 0 and s on our bow. So we had to mark. Oh, did you need me to? No. All right. So what are the implications for our down Nahm transform of this asymptotic holonomy? Well, when you couple e to ls, then you get asymptotic eigenvalues shifted by s in the exponent there. So instead of e to the 2 pi I lambda 1s, you get e to 2 pi I lambda j minus s, etc. And it's easy to show, of course, that ds is in Fredholm when s is not one of lambda 1 through lambda n mod z. Moreover, when it's Fredholm, it's also easy to show that size in the kernel, if size in the kernel of the Dirac operator, then it decays exponentially fast. It's a sort of standard geometric analysis. So the Nahm type matrices we introduced before are in fact well defined. I didn't mention it at the time, but of course xj is unbounded. So we were putting xj between some L2 projections, and since it's unbounded in L2, that could be problematic and is occasionally, but in this case, no, because you're putting it against things that are exponentially decaying. There's no problem defining this. When s is equal to lambda j for some j, then in fact you do get, you can compute that pi is no longer decaying exponentially, and you'll see that you get the famous Nahm poles at each lambda j, and you can compute their order. Okay. So that was, we had, under the holonomy assumption, we had that data. Now, when we're dealing with the bows, we'll also have to have an analog of the holonomy assumption, which we call WAF, without abelian factors. And essentially means that there's no U1 line bundle that splits off, preserving all our data. So under the hypothesis that we have no abelian factors, then we'll define a Nahm transform now going in the other direction. So now I'm going to work with the bow, and I'm going to be looking at Dirac operators in the bow, not Dirac operators on Taub nut. And we'll let pi hat denote orthogonal projection onto the kernel of the Dirac operator of the bow. So that, remember, that's just an ODE now. And that really, the relevant objects here are living not on the parameter space multicentered Taub nut, but on the level set of the moment map, but that just means we have to pass to equivariant sections to define our bundle. So we define some connection nabla hat by taking a pi hat sandwich of the horizontal lift of our D on the to the trivial L2 bundle upstairs, and we'll call the transform in this direction the up transform. So theorem. The up transform, if we have WAF instanton bow data, gives you anti-self dual instantons of multicentered Taub nut. If, on the other hand, if we started off with a ASD connection on Taub nut with generic asymptotic holonomy, then the down transform produces WAF instanton bow data. So we do have a complete circle here. So now we need the analog of the Borel-Veil bot map that we started with. So following Borel-Weber constant, we want to map kappa, which shows that the bundle we started with is equivalent to doing the Nahm transform twice. So this formulation is really close to the original Borel-Weber map, except there's a little bit of a change of variables factor here. Let's let GS denote the appropriate Green's operator for our Dirac operators. Then we define kappa to just be, once again, projection, followed by this distortion factor, the S derivative of our connection, followed by the Green's operator. And that plays the role of, that gives us the requisite map of sections. Plus there are other, for the parts that I've told you about, but for the suppressed data associated with the boundary and transmission data, there are more recipes involving kappa in slightly different ways, but always just with a few factors to the right of it. It's easy to deduce what it has to be. So this, of course, is a map of sections, and we want a map of fibers. And to get to pass from sections to fibers, we actually, if we want to understand where V goes, we take V and couple it to a Dirac mass at the point B in the fiber. And so that, so we're in fact applying kappa to suitable distributional sections. That's not a problem, remember, because the projection operator is smoothing, so it's fine applying a smoothing operator to a distributional section. And so, in a similar manner, you can define a Borel-Weber map for the bow, which maps E to down the Nahm transform composed in the other direction. So we have the following theorems. So if we assume that the instanton, we have an instanton on multicentered Taub nut with generic asymptotic holonomy, then this map kappa that we wrote down constructs an element that's in the kernel of our Dirac operator on the bow. And that kappa is in fact covariant constant and not identically zero. So we get the theorem, we get the corresponding theorem. So on the bow side, if we assume the bow data is instanton and without a billion factors, then if we do the same thing, the kappa hat map maps us to elements of the kernel of the Dirac operator and multicentered Taub nut. So we get an explicit way of constructing solutions, elements of the kernel of the Dirac operator, which is kind of funny. Once again, kappa hat is covariant constant and not identically zero. So corollary, if everybody inside is instanton, and you have either generic asymptotic holonomy if you're in multicentered Taub nut, or if you're WAF if you're in the bow, then kappa gives us connection preserving isometry between the original bundle and it's the second Nahm transform of it. And similarly, if you started with a bow, kappa hat gives you a connection preserving isometry between E with your original bow data and the Nahm squared of that. Finally, we can use these Borel-Weber maps to compare metrics, and we prove that the moduli space of instantons on multicentered Taub nut is isometric to the moduli space of instantons on the associated bow. So that means now that if you're trying to understand the metric of these moduli spaces of instantons on multicentered Taub nut, you can study solutions of differential equations to get information about it. And of course, in the monopole case, that's been done profitably by Bielowski and others. And so this gives you a way to start probing now using just ordinary differential equations, the moduli space of instantons and these gravitational instantons. All right, so as I said, I see a lot of folks there who look even younger than I am. And so let's look at some problems for you all to play with. So first, as I said, we can use these theorems to begin an analysis of the asymptotic geometry of the ALF instanton moduli space by reducing it to studying simpler questions involving solutions of Nahm's equations. Secondly, there's a question of extending this to ALG, ALG star, ALH, ALH star. ALG seems the obvious next thing to hit. Professor Mochizuki tells us that and I'm going to ask him to tell me more about this later, but tells me in the ALG case that we no longer have quadratic curvature decay. And from the standpoint of everything I did, quadratic curvature decay played an absolutely essential role, and I wouldn't know how to do anything without that assumption. So the question is, how do we overcome how does the analysis overcome this hurdle in the ALG case, for ALG star case? A simpler testing ground for two that people were pushing me about last month at a conference is that if we drop the generic asymptotic holonomy condition for ALF, do we still get quadratic curvature decay? So nobody knows this yet. And I'm completely agnostic as to what's true in this case. But if you don't, then once again, how do you overcome the analysis? Somehow you have to have a treatment of this that requires much less asymptotic analysis if you do not have quadratic curvature decay. Finally, I don't remember what I had next, but so the problem that was asked of me earlier, so are there other flavors of Nahm transform if you replace our two-step flag of the Grassmannian with a multi-step flag? Somehow that seems like you should have some different relations among operators, and maybe some transform associated with some supersymmetric coupulative operator, something, I don't know. And next, I guess you could ask about Nahm transforms for manifolds with special holonomy. And so I think I'll stop there. Thank you.
Thanks, Professor Stern, for the excellent talk. Are there any questions? Yeah.
Constructions was for AKLF. What about DK case?
So there the analysis will be the same, but the Bose structures will be different. So that's something that I think is a good problem for somebody who wants to work with the different Bose. But I think the analysis, you'll be able to just take it right out of what we did. That shouldn't change at all.
So more questions? Okay, if not, let's thank Professor Stern again. Thanks.
Thank you.
穹苍广而横千，物合多容，星云。